What's up, everybody? Welcome to the 26th lecture. It is over section 5.3, which is all about this idea of the cylindrical shell method. The cylindrical shell method is another method for finding volumes. And I thought to go over this, I really, am not planning on making this lecture particularly long, because this is something that experientially you're going to have to go through a couple problems on your own. And that is how this particular part of this material works. What I can explain to you, what I can lecture and make a little bit more clear, is where some of the things come from and what the final forms are. And for that reason, this is very much going to be just one of those quick, dirty lectures. Having said that, I thought I'd use the example that the book uses to kind of explain some of this problem, some of these thinkings. Thinkings? The thought behind all of this. So the example the book uses is, it says, let's imagine you've got this shape here. This weird kind of bell curve-esque looking shape. It's the shape formed by looking at the area underneath 2x squared minus x cubed is equal to y. Now we want to take this area, and revolve it about the y-axis. When we do, we get this jello bowl looking thing. Yeah, it looks like one of those jello bowls from like the 80s or something, you know? And we want to know the volume of this. How are we going to find that? Well, we know we could use the washer method, but that's not going to be pretty here. Not really. We could use it, but it's going to take some work. So instead, let's try something else. Let's try the cylindrical shell method. But before we can try it, we need to understand it. And what the cylindrical shell method does is exactly what it sounds like. You're going to take this shape. You're going to break it up into a series of shells. Then you're going to say each of those shells have some width. What happens if we let those widths get infinitely small? So we need infinitely many shells. So we get this shape. How does that work out? Like, what if we use that approach? Seems like a good approach. If we use it, what does that shake out to be algebraically? Like, what does that calculus look like? Well, start off with, let's consider that question in its like most niche details, right? That question assumes that we start off with our original function, and we're going to form these rectangles. Then we're going to rotate those rectangles about the y-axis, as we do in this example. We've got these rectangles. They're centered on some xi value. They have some width, delta x. And we're going to say the height of these rectangles are equal to our function evaluated at that xi bar value. So that's center point, right? That's a midpoint rule. Basically using that sort of an idea to set this up. Now, we're going to abandon the actual geometry of this problem for a moment and just consider what happens when we take and revolve that rectangle around the y-axis. When we do that, we get a cylinder with a hole cut out of the middle of it. And for reasons that I explain really deeply in the lecture notes, the volume of the cylinder comes out to be equal to 2 pi times that x bar I value times your function evaluated at that x bar I value times the width of those rectangles. And basically what happens out, the way we get from all of this to here, is we just take a couple of terms apart, rearrange them, and kind of MacGyver the math until things wash out and we can write it in this form. That's really what's happening. Now I know I'm being really hand-wavy here right now. The reason why I'm being really hand-wavy right now is because I do go into so much detail on how this is found. What I don't do a whole lot of is explain, until we get into the example in the lecture notes, how we use this. Now we're going to use this by saying we have the volume of one of these particular rectangles. I do have a typo on the board that I need to fix. This is the volume VI. So we have all of these cylinders, and we're going to use these to approximate this volume. So by taking the volume of each of those small cylinders and making it so that the width goes to 0 and we have an infinite number of these cylinders, we can add up all of those volumes and arrive at this formula, right? This nice series here. But hey, that's the limit definition of this integral. And this integral is what the cylindrical shell method is. Nothing more to it than that. This is the cylindrical shell method. So how are we going to use it over here? Well, in our problem, in the textbook, in the setup example that it has, the function is this puppy up here. So let's write some of this out. You know that f of x is equal to 2x squared minus x cubed. A is equal to 0. And I don't remember what b is equal to. I'm going to look at the textbook really quick. What is b? Does the textbook tell us what b is? It does not. Wow, okay. Oh, there it is. It is 2. Oh, duh, yeah, that should have been obvious. It's 2 times x squared minus x cubed. Well, for that thing to be 0, x has to be 0. Or another possible answer is x is equal to 2. Duh. Anyhow, so now we know all the relevant information to our integral. Now we can just set up our integral and go. It's that easy. So the volume is equal to the definite integral from 0 to 2 of 2 pi times x times f of x here is 2x squared minus x cubed, and all this is going to be integrated with respect to x. Now from here, we can massage the algebra, do the rest of the work. So we can pull out that 2 pi. We have the integral from 0 to 2. And we can distribute this x all the way through to get that this is equal to 2x cubed minus x to the 4th, integrated with respect to x. And now from here, it's just about evaluating that integral, right? Now, the question everyone always asks, how do I know when to use the cylindrical shell method over the washer method? Honestly, it comes down to whenever one is easier than the other. That's when you use the one over the other. honestly. I will admit that for me personally, historically, this was always the harder one to set up, but sometimes it was the easier one to solve. Sometimes that particular integral came out to be nicer to work with. So that's something to be aware of. In other words, what we've just done here is we've shown two methods to solve the same problem, to find the volume of something that's formed by revolving about an axis. Well, given that, what these two different directions, what these two different methods are telling us is that we can change our perspective a little bit and get the same exact answer with radically different approaches, which is great. It's a great tool for us because the benefit of it is sometimes this is an easier integral to solve, like I just said. I'm going to repeat myself now. This is an easier integral to solve. Sometimes. It might be the harder one to set up, but this is a trade-off, right? Now the other question that oftentimes gets asked is, what do I integrate with respect to? That depends upon what your setup is, right? If you're setting up something in terms of x, you will be integrating in terms of x. If you're setting something up in terms of y, you'll be integrating it in terms of y. Okay, well, obviously, Matt, that doesn't help me much. I'm talking about in terms of rotation. Yes, good question. In terms of rotation. You notice here we're rotating about the y-axis, but we're integrating with respect to x. That didn't happen with the washer method. Washer method, you integrate in the direction of the axis you're rotating around. Whereas in the cylindrical shell method, you integrate to the axis that is orthogonal or normal, in other words, at a right angle to your axis of rotation. So you swap things. That's all. So that's really all I had to say today. If y'all have any questions, by all means, shoot me an email. Come by office hours. What else do I want to say? Oh, there's a couple examples in the notes, or at least one example in the notes on this stuff that I think is a really good motivating question for why they even use it. It's a physics problem that was solved around the time of, like, I guess the early 1800s. So it's something to check out. Again, as always, please be looking at your notes. But this particular problem is just a cool historical problem. With that, that's all I really have for y'all today. So have a good one, everybody. Later.